Good afternoon, my name is Всеволод Юрьевич Евтушевский, and I want to tell you about my mathematical achievements. First, I need to define Young-Fibonacci lattice. It is one of two modular 1 differential graphs. What is modular 1 differential graph? If we have graded rooted graph, it is called modular if each pair of vertices either have one common successor and one common predecessor, or have no common successors and no common predecessors. Also, this graph is called one differential if each number of successors of every vertex equals to number of its predecessors. There are only two this graph, Young lattice and Young-Fibonacci lattice. Young lattice is very interesting, but it's not my topic. And Young-Fibonacci lattice is also very interesting, and it's my topic. Stanley and Fomin began to study it in 1988. What is it? Vertices of these graphs are sequences of digits 1 and digits 2. And in the nth level, there are such sequences that its sum of the digits equals n, and where we have an h. If we can change some digit 2 before the first digit 1 into digit 1, or delete the first digit 1. For example, here we change the first digit 2 into digit 1, here the second, the third, and here we delete the first digit 1. Okay, let modulo of x be the sum of digits of a vertex x, and let further consider two vertices, x and y, such that modulo of y is greater or equal than the modulo of x. My first problem was to count the number of down paths between two vertices. What is yx down path in the Young-Fibonacci lattice? It's a path which begins in the vertex y, consists of some down steps, and ends in the vertex x. I solved this problem, and I have this formula. What is it? Here, f is a function which we describe recursively, but it has an explicit formula with O of modulo of x terms. Here a is an integer from 0 to the modulo of x, and b is an integer from 0 to the number of digits of x. G is a function equals to 1 plus sum of the digits of a vertex y strictly after the g from the right digit 2. For example, we have 2, 1, 2, 2, 1, 2, and 3. Here is the third from the right digit 2. We write 1 plus 2 plus 1 plus 2. It equals 6. Also, z here is the number, not the sum, but the number of digits in the longest common suffix of x and y. And doy is the number of digits 2 in y. This formula contains all of the modulo of x in the power of 2 terms. My second problem was to count the number of s paths between two vertices of Young-Fibonacci lattice. What is yx s path? S path. It's a path which begins in the vertex y, consists of modulo of y minus modulo of x plus s down steps s and s up steps in the sum order. I solved this problem, but before I formulated and solved another problem about delta paths. What is yx delta path? First, I need to define a trajectory. Trajectory is a sequence of non-negative integer number such that the difference between two neighbors of them is plus minus 1. For example, this is trajectory 3, 2, 1, 2, 1, and so on. And what is y-x delta path? For example, if we have this trajectory, vertex y in the third level and vertex x in the first level, y-x delta path is a path which begins in the vertex y, consists of down step, down step, up step, down step, down step, up step, and so on, and the ends in the vertex x. Okay, here E of delta and j is a level which is achieved after the jth up step of a trajectory delta. Okay, I solved this problem, and I have this formula. This formula is similar to the last formula, but it has one more product. And here S of delta is the number of up steps in the trajectory delta. This formula also contains O of the modulo of x in the power of 2 terms. And then, I needed to sum this formula over all trajectories between modulo y and modulo of x, such that they contains s up steps. Okay, and I solved this problem, and I have this formula. It looks huge, but it contains only O of the module of x in the power of 3 terms. Here m is this function, and it was a topic of my diploma work. My work contains 105 pages, and the brief version of it was published in this semester. Okay, and then I continued studying Young-Fibonacci lattices, and my next problem is ergodicity hypothesis. This problem is more serious. What is it? First, I need some definitions. A probabilistic measure on the space of infinite paths from the root is called central if all paths to any given vertex have equal probabilities. The second, a central measure is ergodic if it cannot be represented as a mixture, i.e. continuous convex combination of other central measures. The third, marching boundary is the set of central measures which are limits of the measures induced by the paths of a vertex from certain sequence. Okay, and we have hypothesis. It's all hypothesis of Kerov and Goodman that all measures from the marching boundary in the Young-Fibonacci lattice are ergodic. Okay, what is the form of the marching boundary in the Young-Fibonacci lattice? It was described by Kerov and Goodman. The first measure is the Plancherel measure. It looks like this, but it's not very interesting because its ergodicity was proved by Kerov and Gnedin. And the other measures looks like this. This formula follows not only from Kerov and Goodman, but also from my first formula. Here we have W and beta. W is an infinite sequence of digits 1 and digits 2. Beta here is a real number between 0 and 1. And we have this limit. Here, this sum is my first formula, but with this beta in the power of I. Okay, here that is the number of the digits in the longest common suffix of V and Wn, and Wn is the n last digits of W. Okay. To prove this hypothesis is sufficiently to prove two following statements. The first and the second. the first statement was proved. And I think that the proof of the second statement is similar, but I need to spend more time on this. Thank you for your attention.
Questions, comments?
Yeah, one question is on the previous slide you had d of d of two parameters. What is that, sir?
It's number of paths between epsilon and v. Epsilon is the root.
Ah, okay. Thank you.
How much time exactly do you need?
Ah?
How much time do you need to prove it?
You said you need a little bit of time.
I need more time to prove, but I believe that the proof is similar to the first.
So suppose you prove it next week, what will you think about next?
I don't know. I will ask Fedor Vladimirovich. But writing of it of the first part is something about a month. I will have some to do.
So do you think it will be a publication in a journal, or like when you complete this?
Yes, of course, it's a good hypothesis.
So good afternoon, dear participants of the ceremony, dear colleagues, and today I'm going to talk about what I'm working on, what I have worked on, what I have achieved. And the first result is what we recently finished with my co-authors. This is about sublinear explicit incremental Voronoi diagram. So let us begin with the basics. What is a Voronoi diagram? This is a subdivision if we have a set of sides, this is a subdivision of the plane into cells corresponding to the side, such that the cell consists of points for which the side is closest among all the other sides. The diagram has cells, the diagram has edges, the diagram has vertices, which are just centers of circles passing through three of sides if they are in general position. Also, we will use the notion of pole of a cell. This is a vertex that is just one edge outside of this cell. And there is a known problem of maintaining a Voronoi diagram under insertion of new sides. There is a known linear time per insertion solution for it, and there is a theorem stating that no faster solutions are possible because there may be really many changes per insertion and we have to implement them all. But we can consider another problem, which also has kind of really many applications, to maintain the graph of Voronoi diagram, what is where. And for it, there is no linear lower bound, so we can try to find a faster solution, faster than linear. The only lower bound we have is that there is expected amortized, or just amortized, no more than square root of n combinatorial changes per insertion. So that gives us hope to really get closer to this sublinear time. Let us consider what really happens with the graph of the Voronoi diagram when we insert a new side to it. It undergoes an operation called flarb, which is basically when you replace the insides of a cell with just a blank space. So here you can see a flarb on a real Voronoi diagram after we inserted the side, and its cell is highlighted in yellow. And our point is to implement the flarb as fast as we can, not doing unnecessary work. Luckily, there is a theorem that allows us to, if we found one cell that needs changes, to find its neighbors that also need changes. For it, we have to look at all the pores of the cell and consider if their circles, they enclose new side that we just inserted. If yes, then the cell needs changes. And what is even more lucky is that we have a data structure already that can really quickly report all the circles from the given set that enclose the point. And it supports insertion and deletion of circles also in quite fast time. So it's really usable. The key notion for our work is big cells. So we know that there are not many cells needing combinatorial changes. If the cell is small, we can look at all its neighbors. We won't need to waste many time. And if the cell is less than n to 1/4, that's okay. But for big cells, we will have to design a special method how to handle it fast, not to look at all its neighbors. So let me present you the things we store. It's basically the whole Voronoi diagram in the form of adjacency list. It is dynamic nearest neighbor structure that just allows us to tell which site is the closest to the new one. Then we need special things to handle big cells. The graph of them, how they are connected, to find their common edges, and a couple of structures that will allow us for fast search of vertices inside the cell and its neighboring cells. And after we have the structure, how do we really handle the insertion? We create a queue. Initially, it contains the cell where the new site falls. It is returned by dynamic nearest neighbor structure. And we have all big cells. And for the queue, we look at cells that are already there, and we add their neighbors that need combinatorial changes. And we know that all the cells we need are connected, so that will give us full list of the cells that need some changes to be implemented. After it, we will implement the changes. How do we handle the cells? For a small cell, as I already told you, we can look at every of its PO. There are really not many of them, and add the corresponding cell to the queue. For big cell, we ask dynamic circle reporting structures to point at the cells that we need to add to the queue and add them. After all cells are in the queue, we implement changes, but this is some technical issue that can be just done by some thorough consideration. So if we try to accurately compute the runtime of the procedure, we get such a formula. After a couple of additional lemmas and some deep mind, it is just n to 3/4 up to polylogarithmic factors. So this is sublinear. Yay, we have the result. However, this is nice. This is faster than linear, the first algorithm of such kind. But it still does not meet the lower bound that we have. So after we kind of believed this result, we asked ourselves the question, is it possible to do the thing even faster? So is there a possibility to meet the lower bound? And our idea is to use, this is like my further plan, to use divide and conquer approach, because if in previous case we omitted doing not necessary work because, well, we kind of locate the cells that need changes and handle big cells very fast. Here we would be able to omit doing what we don't need by just locating the places where changes happen quite precisely. And so this is really promising. Let me now just introduce to you the basic setting of what divide and conquer is. On each level we divide the sites into two roughly equal subsets by a vertical line, which is called the dividing line. We can compute the Voronoi diagrams for right and the left sides recursively, but we're still not sure if we need to store them explicitly. What we really need are the following objects. Those are beach lines that are just boundaries of the cell of the vertical line in the global Voronoi diagram. The forests that are parts of corresponding Voronoi diagram beyond the beach line, and those are really the forests, they have no cycles obviously, and the merge curve, which is the line along which the parts of Voronoi diagram meet. And there is a hope, strong hope, that those can be updated really fast, and the search can be also implemented. So hopefully we finish this in the soon future. And the last thing I want to mention is the result that is related to my graduation project that was finished, and then after I defended it, there just some time spent to clear it all up and prepare it for the publication. This is about all the polyhedra that can be glued from regular pentagons. So as we already might know, the gluing is the set of polygons that are equipped with gluing rules, how to glue them together. One polygon can be glued to itself. Vertices of polygons may just not meet, what you can see on the slide. And the very famous Alexandrov's uniqueness theorem states that if the gluing satisfies two very basic conditions, then there is a really single polyhedra that corresponds to it, that can be glued from it. So here you can see what is glued from the gluings on the previous slide. What is the problem? The problem is the proof of this theorem is really non-constructive at all. And there is still the algorithmic question of finding by any means the polyhedron and its vertices and its skeleton that corresponds to a given gluing. And more to that, even simpler cases of this problem are still open. If we already know the triangulation, we still cannot output the coordinates of the vertices, and we even cannot show the skeleton. And the natural idea is to consider gluings that are built of some known blocks using some known methods. One common idea is to use regular polygons and edge-to-edge gluings where basically the edges meet when we glue them together. Here you can see some edge-to-edge gluings of regular hexagons. And our result is that using the technique of enumeration of gluings and some other theorems, you can get a full list of all the polyhedra that can be glued from regular pentagons, their graph structures, angles, vertices, and whatever. What allows us to really produce this list and be sure of what the shapes are there is the theorem that gives us a proximity bound for the polyhedron and approximate polyhedron that can be get by other already known means. After it is proved, we can implement a procedure that really tells us where the edges are of the polyhedron we just glued. So to recap, we have first sublineal algorithm for maintaining the Voronoi diagram, its graph, not like embedded, but just a combinatorial structure. We have full list of all polyhedra that are glued from regular pentagons and what they really look like, how to glue them. And right now, my co-authors and I are working on implementing the really optimal algorithm for maintaining the Voronoi diagram. And for now, thank you for your attention.
Any questions, comments?
Could you say what is your part in this common results? Because normally you have a lot of authors.
Okay, so let me just go from in the order. Here there was an idea, like we sat together, and it was a workshop on computational geometry, and there was an idea to distinguish big cells from small cells. And the word Chen, so the name of this structure, where is it? The name of it also appeared in there. We just, more or less together understood that, yeah, there is the shape of result. Then there was the part of really making sure that it all works. shaping the details. This is not what the seniors really want to do. They like a month ago understood, yeah, maybe there's some kind of then there is the precise work of really making sure that this is a result, and that's what weighed on poor student like me. So I know that is not quite good personal habit, but I would like to say that yes, my part in the result is significant. And here, like, this is not finished, so let's not talk about it. Here we, before I joined the group had already the enumeration. They just needed to make sure, they weren't sure where the edges are. So they had this sack with vertices, and there was like no sure point on where the edges lay, because it wasn't clear from the drawing. The edges were like really kind of flat. So it was on me to to prove that they are really there, to develop the procedure without giving very much hard computation, how to distinguish the edge from just a glitch on the computer.
Questions? Very much. Continue.
Greetings, dear committee and colleagues. Today I will present to you the results of my recent research. My recent research has been mostly concerned with the problem of finding hardest formal languages. But I should probably give a little background of this problem. So, this problem is somewhat analogous to the problem of complete sets or complete problems in general theorem of computational complexity. That is, the sets or problems which accept these sets to which every other problem in the same class can be reduced to. Of course, this depends on the sort of reduction that is applied, like log space, polynomial, many one, Turing reductions, blah blah. But it's and of course it depends on the class itself. Probably everyone knows about things like NP-complete problems and their importance. And here we ask ourselves, what about string parsing? It's technically a sort of computation, and the most widespread way to look at this is by using the reduction by string homomorphisms, which simply map strings symbol by symbol to some strings. This, for example, allows us to devise efficient parsing algorithms, since a reduction by string homomorphism also only is bounded linearly in the length of the output. So, since the time or in space complexities in formal language theory are most often polynomial, a constant doesn't change the complexity. The first such result was obtained by Greibach in 1973 for consecutive languages, which are one of the most ubiquitous classes, of course. And there exists such a contextual language, such that every other, and itself, of course, it can be represented as an inverse homomorphic image. Soon after, it had been proved that deterministic languages have no hardest one, and then so on, like in 1977, Basson and Niva have proved that linear languages, which are a subset of context-free, have also no hardest one, and on, which brings us to the modern times. This is a few of grammar classes, well, mostly grammars. IDPD is an automata, but there are just some of them ordered by inclusion. And here are the results that are already proven. The languages marked in green have a hardest one, the languages marked in red have no hardest one. And here's my addition to this problem. Oh, wait. I think the reader is bugged. It should be highlighted, but yes, you can see. My first foray into this problem was started with grammars with one-sided context operators and languages one-sided context. These grammars extend conjunctive language, which are by themselves an extension of ordinary grammars and are already known to have a hardest language. An extension which allows us to check the substring left of the substring we are currently parsing. And using the already known construction, I have modified it to obtain a positive result for languages with one-sided contexts. Oh, wait. Yes. Then I have examined conjunctive linear grammars, which are a restriction of conjunctive grammars, such that every conjunct is linear, that is, contains both one and terminal. These are also fairly recent, with one caveat. They're fairly recent as grammars. On the other hand, they are actually equivalent to one very real-time cellular automata, or trace automata, which have been researched since the 90s, or 80s. And there are a bunch of results known about these languages, such as their incomparability with context-free languages, and some conditions for the language to be possibly recognizable but as automata or unrecognizable. And one of the simplest non-context-free subfamilies is as follows, with some fixed k. I have, and in my investigation, I have devised a special pumping method for homomorphic images of this family, which allowed me to prove that the entirety of this family cannot be reduced to just one language. And my last research, LLK grammars. These are the grammars which can be parsed left to right, top down, with k-symbols of look ahead and object tracking. They can be parsed in linear time, and they are really widely known. LLK parsers are probably one of the most known formal grammar parsers because they're simple and also quite expressive. Not as expressive as some other linear time parsers like parsing grammars, but still. The thing with LLK grammars is that they actually become more expressive as the parameter k grows. So at the first sight, it would be counterintuitive to expect that all of them can be reduced to one language. And in my research, I have faced an obstacle in the face of in the form of needing to both handle look ahead, that is, read k-symbols ahead, so I can start parsing, and sudden end, because when we reach the end of the string, we need to suddenly resolve all yet unresolved non-terminals to empty strings. But at the end of the string, there is no symbol images and no rules, therefore, from the grammar we are trying to encode. This has been solved by adding end markers, which is actually a rather common assumption, because adding end markers allows the parser to behave like it always has k-symbols of look ahead instead of k or less. And if end markers are allowed, there is a hardest language for LLK grammars. And as a matter of fact, it's an LL1 language that is hardest for all of LLK with end markers. The question is whether such end markers are necessary. Well, I'm currently working on that. But I think they are. And this brings us to the possibilities for future research in this direction, which are, again, numerous. Because it is still not known for every grammar family if they have an hard language or not. For example, unambiguous grammars and their relatives in unambiguous conjunctive, unambiguous Boolean grammars, unambiguous Transjonian grammars, and so on. For none of them, it is known that they contain hardest language or no hardest language, even though the question was posed back in 1977 by Bazon and Niva again. Or alternatively, languages which are defined by automata instead of grammar could also be explored. Since they can also contain a hardest language or no hardest language in their class, like You can see on this. You can even see on this scheme the input-driven pushdown automata on the lower left, which have no hardest language. So the problem is still open. Thanks for your attention.
Are there any questions or comments?
What do these errors on the previous diagram mean, like between languages?
The errors are inclusion. These are language families ordered by inclusion.
String inclusion or string inclusion or just any inclusion? I think that for most of them string inclusion should be known, but I'm not sure. Is every row on this diagram a string inclusion?
Yes. Well, mostly like the middle row, as you can see, is not exactly a full sequence, but every arrow is an inclusion.
And your results are what?
LL grammars have hardest. This is my most recent result, which I am currently working on refining. Then grammars with one-sided context have hardest, which was my first result, and linear conjunctive grammars, or alternatively treeless automata, have no hardest language. I have also tried to investigate if there is a linear conjunctive language to which all linear languages are reducible. But I wasn't very successful in this yet. Like there is a linear conjunctive language that models some linear languages, but not all of them. Well, even when I say some, I say I mean a rather wide class of linear languages.
So you have a counterexample?
No, I do not yet have a counterexample. I wasn't. Yes. Any more questions?
And not, thank you, and let's thank you.
So this talk is I could give a talk about what was in my bachelor's diploma, but I decided this kind of dishonest, so I decided to just give a talk about what follows from my diploma immediately. Okay, more seriously, I'll talk about the background of this whole thing, about an ambiguity of grammars. So first, there is a theory of ordinary and ambiguous grammars, and there are some kind of GF2 grammars which actually you, for the purpose of this talk, you don't have to know what they are. How does the language theory work? Formal language theory work? An alphabet is just some finite set, and the string over an alphabet is just a finite sequence of symbols over such alphabet. Concatenation is just we write the second string to the append the second string to the end of the first string, and formal language is just some set of strings. And there is an operation of concatenation of languages and so on. Concatenation of languages is just the set of concatenations of all pairs of strings, one from the first language, second from the second language, and so on. And usually the main class of grammars that people consider are ordinary or context-free grammars, which work by the following way. Okay, so this you should ignore the cross. Ordinary grammars work in the following way. They have some set of non-terminal symbols which are the symbols of the target alphabet, and some rules which say that we can substitute some symbol by some non-terminal symbol by a sequence of terminal and non-terminal symbols. And we look at all so-called pass trees. Pass tree of what V is a tree in which has a direct tree with every vertex being labeled by some non-terminal except leaves. All leaves are labeled by symbols, so by terminals. And each non-terminal, each inner vertex, has several children which correspond to application of some rule from the grammar. And ordinary grammars are defined in the language defined by ordinary grammar. It's described in the terms of parse trees. What in the language, if and don't leave, it has a parse tree. And GIF2 grammars are some kind of things where we say that tree doesn't have to exist, but rather the number of trees should be odd. So 2 parse trees are not okay. And it is not really important, but what is kind of important is that there are unambiguous grammars, which are which are ordinary grammars where each word has exactly 1 or 0 parse trees. And as it turns out, most of the parses that are really used are unambiguous by design, because they are often even so-called deterministic context-free, which means that they have sparsing with some automata algorithm which doesn't make non-deterministic choices. And so therefore we can talk about some languages that that have some ordinary grammar but don't have any unambiguous grammar. And these languages, in a sense, can be parsed with the simple parses we usually use. And so proving that some language can be parsed by simple parses is kind of negative result. And such languages are called inherently ambiguous. And okay, generating function we will need later. And there are a few ways of proving inherent ambiguity, which we were known before. And I suggest a new way. So we will discuss some. So here we discuss background, how it's usually proved before, and some new results we can prove with our new method. Okay, this Ogden's lemma. It's pretty good. It works well, but it looks like this. Honestly, like if I have really hard time comprehending sequences with have 4 nested quantifiers over 15 variables, and it really has some limitations. It works for well-structured small languages pretty well. It captures uncommutative properties of language also pretty well, in the sense that if you have if you have some word, not only the number of each letter not only the number of each letter in the word is significant information, but the order is also very significant information, of course. But several methods don't work very well with order, so they just ignore it and so on. This method works, but it has several negative qualities as well. It's a very difficult statement, as I said. It's hard to use for large languages in the sense because it involves several choices which we in the end want to lead something to a contradiction. But there is no contradiction if in the end almost all words are in the language, in a sense. So and moreover, it's unsymmetric with respect to several closure properties, and so it's not very cool. So you have some language, you have 2 languages, for them there should be similarly easy to prove their inherent ambiguity. But somehow it turns out that no, it's not similar. For one it's very easy, for this it's almost impossible. So there is analytic approaches. For some subset for some language, its generating function is just a generating function of number of words of length n in this language. And there is a method by flagella that says that we can prove inherent ambiguity by studying analytic properties of generating function, studying its behavior near singularities. And this method works very well for small languages. And it's symmetric with respect to closure properties, but it lacks other things. It's completely ignores non-commutative properties, because here we ignore even the symbols. We just carry bar just about the length. And it fails to work for very simple languages, because for them it simply turns out that while the language is not is inherently unambiguous, but the target function is, say, even linear or something, rational, sorry. Let alone algebraic analytic function. And our approach is just some kind of application of GF2 grammars to prove results for unambiguous grammars. And it use properties of GF2 grammars, and in the end, because every unambiguous grammar is both ordinary grammar and GF2 grammar, because one is both at least 0 or both more than 0 and odd. It proves better. It proves itself better than both of the previous methods for some class of languages. So how it works? It also works very well for small languages. It's symmetric with respect to lots of closure properties, similarly to analytic approaches. And we get many results for the price of 1 in some sense, as you will see in the next slide. And it also captures uncommutative properties to the extent to which we can prove results to GF2 grammars. But it does its worst for the Ogden's lemma, to be honest, and it's willingly ignores some part of information that is available to analytic methods. So it's kind of trade-off. We get something in the middle in the end. And it also uses Crystal's theorem as the most important part. And and Crystal's theorem is really like one of the coolest mathematical statements I know about. And so we will see that, and here, if you new results, the first result is some language, still very simple language. It was not known at all that it's inherently unambiguous. It's the language you can see on the slide. The language of words of A, N, B, M, C, L, where N is not equal to M, or M is not equal to L. So in some sense, complement of A, N, B, N, C, N with respect to A star, B star, C star. This language is hard for both Ogden's lemma and analytic approaches, but our approach handles it just fine. And just by a very simple application, we can get from this language, we very simply move to this language, N, B, M, C, L, where N is equal to M or M is equal to L. Well, it's small language, so it makes sense that Ogden's lemma handles it. But analytic approaches didn't handle it because it's too well structured. And our methods just handle both of them at the same time. And there's also some, and interesting part is that both our methods and analytic methods actually work some kind of similar ways. And there is a kind of analogy between the Crystal's theorem, which is the base result in which our methods are based, and Chomsky-Schutzenberg theorem, enumeration theorem, which is the base result on which analytic methods are based. And there is a similarity when we restate Crystal's theorem in slightly inadequate way, which is actually equivalent. But I just don't recommend to learn it this way. And it turns out that the methods can be extended to the analytic setting, and then we can, if they can be extended, then we can get rid of this setback. And so, that's all. Thank you for attention. Sorry.
Questions?
Well, it's not normal statement of Crystal's theorem, of course. Normal statement of Crystal's theorem, if you doesn't anybody wish to hear it? Okay.
Yes.
Crystal's theorem. Let's say that a sequence of integers is a sequence of elements of some finite set Q, finite set sigma is to automatic. Sequence is to automatic if if we have an finite automaton that reads the symbols or that reads the binary notation of n and outputs the nth element of the sequence. So it reads the n in binary notation and outputs CSN. The sequence is called automatic. Then this so-called algebraic formal power series is just some kind of algebraic object. We have formal power series of variable t, and it's called algebraic if there is some polynomial p, polynomial p with coefficients which are themselves polynomial of t, such that p of f is equal to 0. And it turns out that the algebraic formal power series and the sequence of coefficients power series is algebraic if and only if its sequence of coefficients is to automatic. It's kind of magical because it's kind of hard to see where is the connection between these facts. Between this, in fact, there is like 5 or 6 objects here. So you can say that this statement is just one more object that is another way to state Crystal's theorem. So Crystal's theorem is like several objects that like don't look too much connected. Actually turn out to be the same thing. So it's pretty cool. More questions?
Yeah, I have a question. So is that your plan? So what are you going to do?
Yes, that is my plan.
So you want
So
to investigate this connection?
yes.
Okay.
If there are no more questions, thank you very much and see you.
Okay, so my today's talk is based on a joint work with Nicolas Galuzzi, Dmitry Tsixon, and Artur Rizanov. And our paper is called Bounded Depth Frege, Complexity of Stating Formulas for Graphs. So the plan of my talk will be as follows. First, I will remind you some definitions, and then our paper consists of lower bound, proved by Tsixon and Galuzzi, and of an upper bound, which was proved by me and Artur. And I will tell you about this upper bound, and I will give you a quick overview of the proof. And then I will say a few words about my future plans and research. So what is a Frege proof system? It consists of a finite set of rules, and this set of rules is required to be sound and implicationally complete. A refutation of an unsatisfiable formula phi in this system is a sequence of formulas where first formula is phi, last formula is identically false, and every formula in this sequence is obtained from formulas with lesser numbers by applying one of these rules. And of course, before applying the rule, you can make a substitution into this rule. Proving lower bounds and proof complexity is closely connected to an open question whether classes NP and conp coincide or not. So NP is not equal to conp if and only for every proof system there exists a hard example. And if we take a Frege proof system like unrestricted general Frege proof system, then there are no known superpolynomial lower bounds for this system, so this stands as a major open question. But if we put some restrictions on this system, obtaining lower bounds becomes possible. For example, we can restrict a depth of a formula and a type of gates used in this formula. So as I said, for unrestricted Frege, there is no known superpolynomial lower bounds, and there are also no known superpolynomial lower bounds for circuit and formula complexity. If we take only formulas with constant depth and 3 types of Boolean connectives, conjunction, disjunction, and negation, then circuit and formula complexity, there are superpolynomial lower bounds, they are long known, and so are Frege lower bounds, and these first Frege lower bounds were essentially a generalization of these methods from circuit and formula complexity. But if we add here moduli p gates, then we know circuit and formula lower bounds, but all the attempts to generalize it for Frege proofs have failed, and this is actually very funny. Yes, so this stands as an open question, and an understanding of this kind of Frege system with the constant depth of 3 types of Boolean connectives can be a step to understanding these Frege systems with moduli p gates. So that was about motivation of all this. Now I will define Satan formulas. So we have an undirected graph G and a charging function f, which maps vertices to 0 or 1s. And each edge has a corresponding variable xe. And the Satan formula consists of a conjunction of parity statements. Each parity statement is represented as C and F. And it states that for every vertex, sum of edges incident to it is equal to the value of charging function modulo 2. And it is a known fact that for a connected graph, a Satan formula is unsatisfiable if and only if sum of values of charging function is odd. This is a classical example of a hard formula for many proof systems, so it is natural to study them in Frege proof systems too. So first superpolynomial lower bound for Frege was proved by Aitai, and then it was simplified and adapted for Satan formulas and complete graphs. Then there was a result by Bensasson for expanders, yeah. And then a paper by Pitaisi, Rosman, Sevedi, and Tan. And apparently there is an unfixable bug in this paper, but yeah, that happens. Then there was a result by Hosted with lower bound to the n to the omega of 1 over d for Satan formula on grid with site n. And our paper has a lower bound to the 3 bits of g to the omega of 1 over d, which was a generalization of Hosted's results. It was proved by Itzikson and Kulisi, and me and Artur proved a matching upper bound to the 3 bits of g to the o of 1 over d multiplied by polynomial of the size of the formula. And this result holds for arbitrary graph. So the consequences of this upper bound are first that it gives us a polynomial size proof when a depth of a formula is about logarithm of 3 bits of g. And with the matching lower bound, it induces a strict depth hierarchy for proofs in bounded-depth Frege for Satan formulas. So now I will tell you how this proof in Frege should look like. The first idea which it uses is that there is a compact representation of a parity function on n variables as a formula with 3 types of Boolean connectives of the following size and depth t. And after a bunch of technical lemmas, we are able to efficiently sum equations modulo 2 in Frege system. So if we are to straightforwardly apply this to our Satan formula, which is just an unsatisfiable system of linear equations, we would get a bound 2 to the m to the o of 1 over d, but we would need 3 bits of g here instead of m. Now, I never defined 3 bits of g yet, and I will not, but I will define something similar to it. Basically, these structural parameters define how much our graph is similar to a tree. So 3 partition widths. 3 partition decomposition of graph G is a tree where vertices in this tree are bags, and we split vertices of our graph G disjointly into these bags. And then let's draw all the edges of G on this picture, and if 2 bags are connected by the edge of graph G, let's draw there a thick edge, a meta edge. And these bags and meta-edges should form a tree. A width of this decomposition is a maximal size of the bag in it, and 3 partition widths of the graph is just the minimal width of such a decomposition. And this parameter is nicely connected to 3 widths from one side and moderately nicely from the other side. Here delta of G is maximal degree of the graph. Now let's take a look at how should this proof in Frege look like. We take a 3-partition decomposition with minimal widths, and then the nice thing about it is that if we take one bag, then there are not so many variables incident to this bag. So we can represent all parities corresponding to a fixed bag as a formula with this size. Let me not read it from the slide. So we can derive a local contradiction in the bag efficiently. Then we will be considering cases. So first we take a leaf of our tree, and if there is a contradiction in this leaf, we locate it, and otherwise we know exactly what value of parity we should get on these edges, on these red edges. And then we continue this procedure. We take another leaf and then another leaf. We cut in the leaves, and we are going up to the root of this tree, and then in the end we locate the contradiction in the root of this tree. So all this contradiction may be derived efficiently, and then either 3 widths of G is greater than delta of G, and then this is our desired bound. Or delta of G is greater than 3 widths of G, and then this is polynomial of the size of a formula starting from some constant D. Okay, so open questions which this problem leaves us are: first, it's establishing tight bounds for resolution, because for taking formulas, lower bounds are obtained basically by applying Benson-Wigderson theorem. But if we have 3 widths like n to the epsilon for small epsilon, it doesn't work. So closing this question would require some kind of new technique probably. And a second, like major long-standing open question, is proving superpolynomial lower bounds for random KCNF in bounded depth Frege. And now I will say a few words about my future plans in research, I guess. So now I'm focusing on algebraic proof systems, such as Null-Stalinisation and polynomial calculus. And like one of the main reasons they were introduced is to deal with this mod P gates in bounded depth Frege, because these systems are not like this bounded depth Frege without mod P gates. They can sum things up, these systems, so that could help to understand Frege with mod P gates. In my bachelor thesis, I have a result connected with Null-Stalinisation proof system, and now I'm currently trying to strengthen it. And I wrote about it in this A4 page I sent to jury. Okay. And the second subject that interests me is 1 plus KBPs. 1 plus KBP is a branching program where we can test variables on each path no more than once, but we can test up to k variables like arbitrary number of times. And the deal with these things is that we have lower bounds for functions. But if we are to consider this as a proof systems, we would need lower bounds for formulas. And that's what I'm currently trying to do. Thank you for your attention.
I'm first wondering, like, did you present this result already? Did it appear somewhere, or did it?
Frege thing.
Yeah.
Yeah, it's published already. MFCS. Yes.
Okay. And second question. So what exactly are you going to do with the first items?
With algebraic proof systems. Okay, so my result from bachelor thesis was based on a result by Beam and Ries, which gives a separation of multidifferentiation of different fields. So they had a formula, not a formula, but system of polynomials, which is easy over reals, but hard over FP. So, but this separation is like n to the epsilon for small epsilon. It would be nice to obtain a linear separation, and it would be nice also to generalize this to polynomial calculus. Yeah, and in my bachelor thesis, I kind of transformed this system of polynomials into a legit formula, because this thing that was in their paper, it wasn't representable as a CNF of polynomial size. Mm-hmm.
More questions? If not, pretty much
Okay, hello everyone. Today I will talk about my bachelor thesis. The title is on the group determinant. Oh, arrows. This is a background. This is some standard fact from the textbook. If G is a finite group, V is a finite dimensional vector space over C, and this is phi trivial representation. We know that character will determine, plays a very important role in the theory of representation. This is standard, but in the history, because here the character is the trace of the action. Sometimes, originally in the history, mathematicians considered more on the determinant. This is what I want to talk. Oh. And it has a reference. And the second definition of in the history, I think maybe I should use this. Okay. Consider the left action of a general element in the group algebra. We write x as a sum of indeterminate of x, xg. Then the left multiplication is defined by this. Oh, I'm sorry, I lost some v. Oh. Lost some v is ux v to v maps to. By this action is a linear transform, so we can define its determinant. We can say that determinant of mu x is a polynomial in xg, and this polynomial we call it the norm of this representation. And if v here is kg itself, it is just a regular representation. This is called the group determinant. And some properties, maybe the properties is more interesting. If the representation is irreducible, then the norm is a irreducible polynomial. And if two representation is isomorphic, then the representations are isomorphic, then the norms are the same. And these two properties are actually proved by modern theory. Before Frobenius created character theory, people do not know this. After that, we know that they use the structure of semi-simple algebras, and they prove this. And I think the most interesting thing is the group determinant will determine the group structure. It means if you have a polynomial that is a group determinant, then it has only one group structure to make the group determinant to be this polynomial. That's the reason why we want to compute it. And this is a reference that the group determinant determines the group structure. And then an interesting lemma, okay, let me read it. Let sigma from the matrix algebra to the matrix algebra itself, and isomorphism as a linear space, mapping the invertible matrix to the invertible matrix. Then sigma must be one of the following case. It is left and multiplication by an invertible matrix, or differ by an differ by a transposition. This looks like a linear algebra exercise, and yes, it can be, but in the history, Frobenius knows it, but the reference is very hard to read. Not hard to read because we know that Frobenius passed away. The paper is published after his death, so no one knows what is written, and it's in German. And the second, Dieudonné knows this. He proved it in his paper, but he used 5 pages of his paper to prove this, and you can say the title is very strange. Do not aim at this. So I reprove this. I reprove this, given very beautiful, I think, beautiful proof. And this is the first work I do. And then the second thing is there is a very important concept in the group representation in history, at least. It has a very good relation. It has a strong relation between the group determinant. We determine the L character to be the representation, to be the coefficient. We know GL is L copies of G. And then G1 to GL maps to the coefficient of X1. This is a monomial X1 to XL in this action. And this is actually is a brief for this mu x and x equal to 1 plus x. X1 G1 plus XL GL. It is a determinant of this, where X1 to XL is a determinant. And the relation is this. The L character can be can determine the norm. More precisely, the coefficient of this, we know that X1, K is the index, and NG is index. The coefficient of this is determined. We have an expression for this. It's determined by N character. This is a connection, and I cannot find any reference for this formula. It's not hard, but okay, it can be my work, but it's never found in some reference book. And my result is this formula. First, we introduce some notation. When S equal is a subset of 1 to L, this 1, 2, 3 up to L is from I to J. Then we denote GS by the multiplication from GI to GJ. And for G1 to GJ, I get a note that here is a classification or division of this set. Then we can express the multiplication of our original character to the sum of the division. And the division, we know that for L, it only appears once. It is just cut point by point. There's a division point by point. So we get a recursion formula for the L characters. And this thing, I think, in the history, Frobenius proved this thing. It looks very easy, but you cannot find this fact. We know that it's not we know that it is a property that when we exchange them, the value do not change. But in his formula, we cannot say it from his formula. But you can see it in my formula because it's completely symmetric. Of course, in some sense, they are equivalent. But what is very special thing is this formula do not have an English proof. I mean, maybe Frobenius knew this formula and written in his script, but it never appears in any English paper, at least as far as I know. So some examples. For example, the first character, one character is just the original character. And the second the expression by our formula or some is well known, is known by somebody that the character of GH is expressed by this, and this may be more familiar to some mathematician working in representation theory, because it is actually this thing is well known for linear algebra students. Maybe for freshmen, maybe some of them know this, but generally this thing maybe no one knows for freshmen. So in some sense, what I proved is a generalization of such formula. Actually, the main theory I think is this one is my work. Okay, 无需要. That's all. Thank you.
Yeah. You say that the determinant defines the group uniquely, yes?
Yes.
So is there some kind of analogy of Fourier transform that can be based on? There is a Fourier transform for commutative groups. So just
you mean?
Can you base some analogy of Fourier transform on the determinant of the group?
You mean abelian group, right? Abelian group.
For non-abelian groups. So for abelian groups, we have usual Fourier transform, which is just very easy to compute very quickly. You can compute it quickly. And if we try to do the same with representations for non-abelian groups, then we can have large matrices, and handling large matrices is even harder than handling the original group. But maybe there is something like for determinant, and I'm not sure. So
I'm not not
so
sure.
If you don't know, it's okay. Just a question. If you maybe you know, it would be interesting if you know and you can answer the question.
Well, I don't know. And for abelian groups, there's some interesting thing. This is the group determinant is exactly the cyclic determinant. Maybe it's well known.
Okay.
It's well known that you compute A. Maybe to C.
What's usually circulant or something? Yes. Is this thing usually called circulant or something? I'm not sure. Is it problem? Okay.
You want?
You mentioned a statement about the matrix and linear map complexes relations. Can you please briefly explain the proof?
The proof of what?
You have a statement.
Yes.
Can you please?
You mean this one? This one. First, you need to use some theorem I never hear, but I don't know how to pronunciation this theorem. Use this theorem. You get firstly the determinant is some kinds of preserved, and you prove that the rank is preserved. The rank is preserved. Then you find something like the arrows, the columns and the arrows of P and Q. Then you do some normalization, then it works. That is my proof. But for them, I read Frobenius. No. I read Dieudonné's proof. His proof is very horrible because he do not use standard language. Maybe that's the reason he published it in French, maybe not in English. Well, it's very common. If you don't want to let some more mathematician find problem with you, then you publish in your own language. Yes. I think it is a small research, and general. I think it cannot be further, or for me, it's not that valuable to get more further. So I want to find something new to do. So yes, everything. Okay.
Thank you.
Okay.
So, as the slide says, my talk will consist of two parts. First, I'm going to talk about the problem I had in my bachelor's thesis, which a couple of months ago became a paper. And then I'm going to talk about the problem I'm working on at the moment. So the first part is faithful actions of ADE rate groups on triangulated categories. And let me begin by introducing the setting and giving a few definitions. So throughout the talk, K will be an infinite field, and D will be an enhanced K-linear triangulated category. For example, it could be an algebraic triangulated category, which is not very restrictive because all triangulated categories appearing in algebra and geometry are algebraic. And from this additional condition on my category, I need the following. So first, for every object x of D, I want the derived home complex functor R home from D to the derived category of K vector spaces. And I want it to have a right adjoint. Secondly, I want functorial cons of natural transformations of functors. So in this context, one can define for every object x of D the spherical twist functor Tx along x, which is an endofunctor of D defined by the following formula. So this is just the con of the co-unit of this adjunction here. This definition is due to Zeidel and Thomas, and it was originally motivated by homological mirror symmetry. So in general, a spherical twist is not an autoequivalence of D, but it is if X is a so-called spherical object. So let me give a definition on the blackboard. Let omega be an integer. We say that an object X of D is omega spherical if the following three conditions are satisfied. So first, for every object P of D, the total home space from P to X is finite dimensional. Now, secondly, there is this condition that says that the X algebra of X is the same as the cohomology of the sphere of corresponding dimension, but formally I want the following condition: home star XX is isomorphic to K of T quotient by T squared as graded K algebras, and here the degree of T is omega. So this means that this home space is two-dimensional and concentrated in degrees 0 and omega. And for omega equal to 0, there is this additional condition that we need. And the last condition is the Calabi-Yau condition, which basically says that X is omega Calabi-Yau, which means that for every object P of D, there is a perfect pairing defined by the composition. X P Px home star X X. So here we have to quotient out by the identity. So this is isomorphic to K. This is just the composition. So this is a perfect pairing. Yeah. If X is omega spherical, then Tx is an autoequivalence of D. Now let gamma be a simply laced Dynkin diagram, and we can define the Artin group of type gamma, or the generalized rate group, which is defined by generators and relations in the following way. So for every vertex of gamma, we have a generator Si for every vertex I. If we have two adjacent vertices I and J, then there is a braid relation between them. And if two vertices are not adjacent, then the corresponding generators commute. Then a gamma configuration of omega spherical objects is a collection of omega spherical objects enumerated by vertices of gamma with the following condition on home spaces between them. So if we have two adjacent vertices, I and J, then home spaces between the corresponding objects in this collection Pi and Pj is one-dimensional from here to here and from here to here. And if there is no edge, then all homes are 0. And Zeider and Thomas showed that if we have a gamma configuration of omega spherical objects and we consider the twist functors corresponding to this object, then they satisfy braid relations of type gamma up to a natural isomorphism. In other words, we have a group action of B gamma on our category D. And now one can ask if this action is faithful. And the main result of my thesis, and now a reprint, is that this action is indeed faithful for all gamma, all D, and all omega not equal to 1. And why do I like this result? First of all, it is known that for omega equal to 1, this action can be hot faithful. So in some sense, this theorem gives the final answer to the question. And secondly, this question is not new at all. As you can see, I've listed some results that appeared over the past 20 years. So faithfulness of this action has been established for some special cases before, but none of the methods suggested before were suitable to prove faithfulness in full generality. And in our paper, we present a new approach that enables us to generalize all of the existing faithfulness results, and also to do it almost simultaneously for all cases. And also, for example, for omega equal to 2, when faithfulness had been known, our proof is a lot simpler than the existing one. Okay, so now for the second part, which is about the derived Picard groups of representation finite self-injective algebras. So as before, let me begin with a few definitions. So let A and B be finite dimensional K algebras, K is still field. So we say that they are derived equivalent if the bounded derived categories are equivalent as the triangulated categories. So this is a natural analog of the classical Morita equivalence. It is strictly weaker, but it's still a nice equivalence relation. It reserves many structures associated to an algebra. Also, there is a natural analog of the classical Picard group, the derived Picard group. of an algebra, which is a group of so-called standard autoequivalences of DBA, modular natural isomorphisms. I will not give a formal definition of a standard autoequivalence. Well, this is an autoequivalence of the following form, but I will not say what is a Hilton complex. But the thing is, nobody knows if there are any other autoequivalences apart from standard ones, so you can just think of it as the group of autoequivalences of DBA. These groups are very hard to compute. The complete descriptions have been obtained only in a few cases, unlike the classical Picard group. Now, what is a self-injective algebra? We say that A is self-injective if every finitely generated projective module over it is injective, or equivalently that A is injective over itself as a module over itself. So this is a nice class of algebras. It's wide enough to contain many interesting examples. For instance, group algebras of finite groups. But on the other hand, it's small enough to study because self-injective algebras share some interesting structures and features. Yeah, so it's a nice class. So up to derived equivalence, they have been classified by Asashiba, roughly saying that, they correspond to some data, including a simple Dinkin diagram, so roughly saying they're split into three groups, A, D, and E. And for type A, the derived Picard groups were described by my advisors, and my plan for the nearest future is to do the same for the remaining algebras. And the last thing I want to do is I want to establish a link between two different things I talked about today, and also provide an example or an application of the main theorem of the first part. So for this example, assume K to be algebraically closed and consider the following algebra. So this is the path algebra of the following quiver. Here is the quiver, and relations say that any path of length more equal to 2 is 0, except for these cycles of length 2 that start and end in the same vertex. And such cycles that start at the same vertex are equal. So this cycle equals this cycle. Okay, so this is a finite dimensional algebra. It is a representation finite self-injective algebra. And if we consider indecomposable projective modules associated to vertices of the quiver, it's easy to see that they form a Dn configuration of zero spherical objects in the bounded derived category of this algebra lambda. So we know that there is an action of this group of type Dn on this category. And by our result, we know that this action is faithful. So we conclude that spherical twists along this indecomposable projective modules generate a subgroup of the derived Picard group of lambda. And the conjecture is that, in fact, the derived Picard group is generated by this Artin group, modulo the classical Picard group, and shifts. And who shows this? This is my plan for the nearest future. Okay, thank you. That's it.
Any questions, comments?
Okay.
Let's extend the speaker again.
Thank you.